7.2. Apply exponent properties involving quotients. Quotient of power property is defined as a to the m over a to the n equals a to the m minus n, where a does not equal to 0. And m and n here are positive, where m is greater than n. Let's prove this using two numbers. I'm going to let m equal to 5, n equal to 3 for a to the m over a to the n. Then, after we substitute 5 for m and 3 for n, I can factor a to the 5th power by writing a times a times a times a times a, and the same thing goes for a to the 3rd power, a times a times a, and then I can cross out 3 pairs of a's. So I will be left with a times a, which is a squared. And a squared is just a to the 5 minus 3, which corresponds to m minus n. And for the second case here, if a to the m over a to the n equals 1 over a to the n minus m, where a does not equal to 0, then m and n are also positive, where m is less than n, meaning n will be bigger than m. Let's prove this. A to the m over a to the n equals a to the m over a to the n times 1 over a to the m over 1 over a to the m by using the identity property of multiplication. Now this will just be equal to 1. So now I can take a to the m and multiply that by 1 over a to the m, which equals to 1. And I can take a to the nth power and multiply that by 1 over a to the m power to get a to the n over a to the m in the denominator. And then I can rewrite this as 1 over a to the n minus m. And now for this next property, power of a quotient property, I have in parentheses a over b to the m power. Now I can share this m with a and also share this m with b, so I get a to the m powered over b to the m power. Let's prove this by letting m equal to 5. Then a over b to the 5th power, I could factor this by writing this 5 times. And I can multiply all the numerators, so that will be a to the 5th power, and I can do the same thing for the denominator, and that would be b to the 5th power. So this would equal to a to the m power over a to the n power. And here a and b are real numbers with m greater than 0, meaning it's a positive integer. Okay, part A, simplify the expression. First, we need to take this exponent of 3 and share it with the numerator and the denominator. And then I'm going to use a previous property we learned, ab in parentheses to the m power. I need to share the m to each of the bases. So 3 with 4, so I will rewrite that as 4 to the 3rd power, and x squared in parentheses to the 3rd power. I'm going to take 3, 5 to the 3rd power times y to the 3rd power. So 4 cubed would give you 64, and 2 times 3 here give you 6. Okay, we're using this property. And 5 cubed will give you 125. And right, y cubed. And for this next one here, I can first write the next step as -1 in parentheses to the third power times 5 over y to the third power. So basically I share the power of 3 with -1 and 5 over y. So this will be negative. And again, I'm going to share this again, 5 cubed over y cubed. So this will be negative 125 over y cubed. Okay, for this next one here, I can share the 2 with the numerator, 3a cubed. We put parentheses around this, squared. And I can also share the 2 with the denominator 2y. I will recopy 1 over a squared. And now I need to share the 2 with each of the factors in the numerator. 3 squared times a cubed to the second power over 2 squared times y squared times 1 over a squared. Okay, in the next step, I'll take 9 a to the 6th power 4y squared times 1 over a squared. And then I can simplify a to the 6th power and a squared. And by canceling a squared in the denominator, and this would be a to the 4th power. So you have 9a to the 4th power over 4y squared. Okay, for this next one here, there's a -1 factor in the front, so I can share the power of 3 with -1, as well as 5 and x times 2x to the 4th power to the 3rd power over y cubed to the 3rd power. Okay, I share the 3 to both the numerator and the denominator. Okay, let's take this one factor at a time. -1 cubed is still negative. 5 cubed is 125 over x cubed. And I need to share the 3 with each of these factors. So 2 cubed is 8. And then x to the 4th power times 3 is x to the 12th power. And the last one, y to the 9th power. Now I can simplify x cubed with x to the 12th power by canceling out x cubed in the denominator. And in the numerator, it will be x to the 9th power. So your answer will be negative 125 times 8 is 1,000 x to the 9th power all over y to the 9th power. Okay, I'm going to start skipping some steps now. Okay, first you need to share the 3 with the numerator and the denominator. Okay, and because there are 3 factors here, I still need to share the 3 with each of these factors. So 2 cubed gives you 8. And m to the 5th power times 3 gives you m to the 15th power. And then this would be n cubed. The 4 to the 3rd power will give you 64. And n squared times 3 will be n to the 6th power. And I would do the same thing for the other factor. I have a negative here. I need to take that into consideration. Negative 1 times to the third power is still negative. And I need to share m with each of these factors. So m cubed, n to the 12th power, and 5 cubed would be 125, and then n cubed. And then now we can simplify. First of all, I'm going to first take care of my signs. Positive, negative, negative. Simplify 8 with 64. I'm done with the numbers, and I can multiply 8 and 125 to get 1,000 in my denominator. Okay, now I'm going to deal with the variables. M to the 15th power times n to the third power is m to the 18th power. And I'm going to look at all my n's now. N to the third power times n to the 12th power is n to the 15th power, and for the denominator, n to the 6th power times n to the third power is n to the 9th power. But we're not done here. We need to take 15 and subtract 9. So that would be negative m to the 18th power times n to the 6th power all over 1,000. Part B. Find the missing exponent. Okay, let me first simplify the left-hand side of this equation. I have a question mark here, and that's what we're looking for. So I can share the question mark with the factor of 6 and the factor of x to the 5th power, so that will become x to the 5 times the question mark times the x. And I'm going to set that equal to 216 x to the 16th power. Now I have two pairs here, 6 to the question mark with 216, or this pair. And I'm going to use 6 to the question mark equal to 216. By short division, I know that it takes 3 6s to form 216, so my question mark will be 3. I'm going to confirm this. I'm going to take 5 question mark plus 1 equal to the power of 16 here. 5 times question mark equals to 15, and question mark equals to 3. Okay, and this next one here, again, I'm going to share the question mark with each factor here. So 2 to the question mark times x 5 question mark times 7 squared times x to the 14th power, 392. I'm just going to copy this. Now I'm going to rearrange my numbers. So this will be 2 to the question mark times 49 x to the 5 question mark times x to the 14th power. Okay, so again I have two pairs. I can either set this part equal to 392 or this part to x to the 29th power. We're going to do both. So 2 to the question mark, 392 divided by 49 is 8. And it will take 3 factors of 2 to form 8. So question mark equals to 3. Let's double check. 5 question mark plus 14 equal to 29. 5 question mark equals to 15. Question mark equals to 3. Yay. Part C. Find the values of x and y if you know that b to the x over b to the y equals b to the 9th power, and b to the x times b to the 2 over b to the 3y power equals b to the 13th power. Now, for this first one here, I know that I can rewrite this as b to the x times b to the negative y equals b to the 9th power. So I can take the exponents down and set up an equation here. X minus y equals to 9. And the same goes for this case. I can take x plus 2, subtract 3y, because I want to move 3y to the numerator, I need to change the sign and set this equal to 13. So this would be x minus 3y equal to 11. Now I can use the system of equations to solve now. Okay, and rewrite this over here. X minus y equal to 9. X minus 3y equals to 11. And I'm going to use the elimination method by subtracting these equations. X goes out, and then I'm going to solve for y. Negative, negative, positive. 3y plus minus 1 is positive 2y. And then negative 11 plus 9 is negative 2. So y would equal to negative 1. And I'm going to use this equation here. I'm going to substitute y for negative 1. So x would equal to 8. And these are my answers. The fractal tree. To construct what is known as a fractal tree, begin with a single segment, the trunk, that is 1 unit long, as in step 0. Add 3 shorter segments that are half unit long to form the first set of branches, as in step 1. So the length of each of these branches is only half as long as the trunk. Then continue adding sets of successively shorter branches so that each new set of branches is half the length of the previous set, as in step 2 and 3. So the length of this little branch here is half the length of the previous set, and so forth. So part A, make a table showing the number of new branches at each step for steps 1 to 4. Write the number of new branches as a power of 3. So in step 1, we have 3 new branches. So I can write that as 3 to the first power. And for step 2, I have 9 new branches. So I can write that as 3 squared. And for step 3, I have 3, 6, 9, 12, 15, 18, 21, 24, 27 branches. So I can write this as 3 cubed, so and so forth. And the next one would definitely be 3 to the 4th power. Part B. How many times greater is the number of new branches added at step 6? So I'll go along with step 5 now. That will be 3 to the 5th power. And by step 6, you'll have 3 to the 6th power. And I can rewrite this as 3 to the 5th power times 3 to the 1st power. So the answer will be 3 to the 5th power times. In part A, write the lengths of the new branches at each step as a power of half. What is the length of the new branch added at step 9? So from step 1, the branch is half of the length of the trunk. So I'm going to write half to the first power. And in step 2, this length here, the length of the branch here is going to be cut in half again. So that will be 1/4. So I can write that as half squared. And the pattern continues. Half cubed and half to the 4th power. And if the pattern continues, by the time I get to step 9, it will be half to the 9th power, which equals to 1/2 to the 4th times 2 to the 4th times 2. I'm just breaking this apart so I can multiply this more easily in the denominator. And the length of the little branch in step 9 will be 1/512. The brightness of one star relative to another star can be measured by comparing the magnitudes of the stars. For every increase in magnitude of one, the relative brightness is diminished by a factor of 2.512. For instance, a star of magnitude 8 is 2.512 times less bright than a star of magnitude of 7. So that means if the magnitude of one star goes up, the brightness of the star drops by a factor of 2.512 times. Okay, the constellation Ursa Minor. So this is the constellation, group of stars. The Little Dipper is shown. How many times less bright is Eta Ursae Minoris than Polaris? As you can see, the magnitude for the Eta Ursae Minoris is 5, so this star has to be less bright than Polaris, which has a magnitude of 2. So I can take 5 and I can subtract that by 2 to get 3. So I can take this factor here and write it to the power of 3 and say that Eta Ursae Minoris will be 2.512 to the 3rd power less bright than Polaris. And this concludes the lesson.